In our last video, we saw some examples of where modular arithmetic would occur in real life. What we did not necessarily discuss was integer division, or where it falls into the mix of this. So what I'd like to do is a little bit of a more formal introduction to what integer division is and why it's necessary, and then let's move into how that relates to the mod operator we've seen examples of. Now, each of the operations, addition, subtraction, multiplication, and regular division, work on the integer data type just as they did on the floating point data type. However, there are times when we'll want to perform integer division, which quite simply is the exact value of regular division, but rounded down no matter what the decimal place might be. So even something like 1.99999 as the result of a division, if that were done with integer division, would be rounded down to 1. The real benefit of integer division is that it takes as input integers a and b and produces as output another integer. So if you'll take a look at what we have coded down below, I've defined two variables, numerator and denominator, and I'm going to do a division with them. If I use regular single / division on numerator divided by denominator, even in an example where we have an even division, 6 is evenly divisible by 3, the program prints an output as 2.0, which is typically how we would write a floating point value. And then if we ask Python to tell us the type of the object that results from this regular division, even though the answer is a whole number, Python tells us that that value is a floating point value. So whenever we perform a regular division inside of Python, even if we use an integer here and an integer here, and this number is evenly divisible by this number, the output that we get here will always be a floating point value. If instead I would have asked the computer to do numerator / denominator, so two division signs, I still get an answer of 2, and you note that Python doesn't put the 0.0 after it, and when I ask for the type of that object, it tells me that I have an integer here. So if I were in a case where I need to start with two integers and perform a division, and I need to get an integer back, I need to use this integer division. The next example reassigns a value of 5 to the numerator so that the division is no longer an even division. And you'll see that when I here do numerator divided by denominator, it tells me a floating point value, which is what I would expect it to do because 5 is not evenly divisible by 3. However, it's when I do this integer division, you'll notice that this 0.66666 has been entirely truncated. When I ask Python to do integer division on 5 divided by 3, it throws away the entire decimal, even though mathematically we would typically round up if the decimal is greater than 0.5. A computer will throw it away no matter what the decimal is and just take the part that comes before the decimal point. So that's how integer division works and precisely what is being done when you perform integer division. Let's now talk about that mod operator formally, and the command for that mod operator is a % in Python. Now, let's think about when we perform integer division on two integers a and b. Let's let q be the integer that arises when we do that division. What is true is because we are taking the floating point division, a divided by b, and always rounding it down, no matter what, this resulting integer division will always be less than or equal to what I would have gotten if I did floating point division. And what that means if I multiply both sides of this equation by b is that this integer division result multiplied by what we're thinking of as being in the denominator is less than or equal to what happens when I do this floating point division and then actually multiply by the denominator, and I get an a back. In other words, there's a difference between the value I started with and this integer division multiplied by b. What we're actually getting when we perform A modulo B is precisely the difference between A and this value QB over here. Sometimes the way I like to think about this is with an example. Let's imagine that you have something like apples and you're distributing 5 apples to 3 of your teachers, and you want to do so in an even way, but you don't have a knife to cut any of the apples. You'd go around the room and give each teacher 1 full apple, and then you wouldn't have enough to give the teachers another round of apples. So those 2 apples that remain would be your remainder. The number of apples each teacher got would be equivalent to this integer division, and because we weren't going to split up those remaining apples are found by looking at A modulo. So I've done a couple of examples here just to solidify what we're talking about. If I looked at 6 modulo 3, what is the remainder when 6 is divided by 3? Well, there isn't anything left over, because if we had 6 apples and 3 teachers, each teacher would get 2 apples and there wouldn't be any left over. We have a beautiful even division. So when we have an A value that happens to be evenly divisible by the B value, the result of this mod operator will be a 0. There isn't any left over, and that happens precisely when our A value is evenly divisible by our B value. Otherwise, if things are not evenly divisible, there's some leftover. If I had 25 apples and 6 teachers, each teacher would end up with 4 apples and 1 apple would remain. Now, just to drive home how the integer division and the modulus work together, if I looked at something like 199 integer division by 100, we know regular division would give us 1.99. Remember, we don't care how close that value is to 2. The integer division is going to round that number down and just give us a 1. And so we're going to view 199 if I had 199 apples, lots of apples, I get it, and 100 teachers. Each teacher would get 1 apple, and I would have to have those remaining 99 apples left over. So you can see here too that your modulus will fall anywhere in between 0 and 1 less than the thing you're modding by. If I had even 1 more apple, then I would go back to this case of 0 with a remainder, because each teacher could evenly get 2 apples and then we would have none left over.